Time for us to do some practice with problems which involve cylindrical and spherical coordinates. Because they're a little bit different, it is very useful to go through and do practice because it helps build intuition. And we need that intuition to be able to use them. And this will come up in a later part of the course, being able to describe things in a different coordinate system to help make problems easier. And don't we like it when things get easy? So it's important to put some time in now to really get our minds to start thinking over things. So do the problems. And if you're following along with the video, make frequent use of that pause button. See a problem? Pause. What would I do? How can I work the problem? And try it out. And if you need help, I'll come join you. Just unpause and I'll be right there to help you. All right. Well, let's begin. So our first problem. Rewrite x squared plus y squared plus 4z squared equals 9 in spherical coordinates and solve for rho as a function of phi. Now you might say, is that a sphere? And the answer is no, it's not a sphere. How do we know it's not a sphere? That's good to know. You see that that's a 4. It doesn't match the coefficients in front of the x squared and the y squared. So what we actually have is something called an ellipsoid. It's like an ellipse, but more oid. Three-dimensional form of an ellipse. All right, so that's all right. We'll get into that in another session, what we mean by that. So for now, what do we need to do? Well, we know we're in Cartesian coordinates. The reason I say we know we're in Cartesian coordinates is because we have x, y, z. Those are what we use for Cartesian coordinates. We need to switch to spherical. So what are sort of the key things? Well, the key things to keep in mind are x squared plus y squared plus z squared equals rho squared. And that's sort of a really nice key idea. In fact, this is one of the things that we'll oftentimes notice when we're dealing with spherical coordinates in the future is, x squared plus y squared plus z squared compresses in a very nice way. All right, what are the other two? Well, we have that x is, not x, z, is rho cosine phi, and r, if we need it, well, that's rho sine phi. Okay, so that's what we have. Now, you might say, couldn't we have written down x? In fact, we can. We know x is r, which is rho sine phi, cosine theta, and y equals r, rho sine phi, sine theta. And what you could do at this point is you could say, well, I'll replace x, I'll replace y, I'll replace z, clean it all up, life is good. But it sounds like there's going to be a lot of work involved. So before we do a lot of work, let's ask ourselves the question, are there some easier things we can do to get the same effect? Now, one of the things we should be looking for is when we're dealing with spherical coordinates, we should be looking for that x squared plus y squared plus z squared, because there's just that beautiful collapsing. So this is our favorite thing to look for. And we ask ourselves the question, well, do we see an x squared plus y squared plus z squared? And I can understand people who might be hesitant and say, oh, we're so close, but the 4 is messing us up. But remember, we have the ability to rewrite things so that they're easier to work with. So maybe we can rewrite what we have right now. So let's think about it. We could write that as x squared plus y squared plus z squared, where I pull off a single z squared. Well, how many z squareds are left? Well, 3 more of them. So plus 3z squared equals 9. Now, what comes next? Well, the x squared plus y squared plus z squared, rho squared, clean. We didn't have to use this x equals rho sine phi cosine theta. Nope, simply became part of that rho squared. Now, you might wonder, what if we had done that x equals rho sine phi cosine theta? Why, dot. Would we end up with the same answer? Yes, eventually. You have to be a little bit patient, but you'd see lots of sine squares plus cosine squares, and you start to be combine. All right, but back to our regularly scheduled problem. How about this last piece, this 3z squared? Well, that's 3 rho cosine phi squared and equals 9. Note, I'm being very careful in adding parentheses here. The square is affecting both the rho and the cosine, not just the cosine. So this becomes rho squared plus 3 rho squared cosine squared phi equals 9. Now, you'll notice there's two terms here, and they both have rho squared. So rho squared times 1 plus 3 cosine squared phi equals 9. And now we're getting close. See, we're in great shape right now. In fact, this is one of the best places that we can be in the following sense. You'll notice there's this instruction, solve for rho as a function of phi. So whenever we're asked to solve for rho, that means we really want to get one row to rule them all, one row to find them, one row to bring them all, and in the light of calculus, bind them. And we have just one row right there. So we can get that single row by itself. So we say, all right, great. So rho squared is 9 over 1 plus 3 cosine squared. And now we say, all right, take a square root. Now you might say, do we need to worry about plus or minus? And I'm going to hedge my bets and say, realistically, no, you shouldn't. And only if you have a really mean teacher, and I'm not one of them. The reason I say realistically no is most of the time we don't think of rho as being negative, because rho should be how far out you go from the center. So rho should be a non-negative non-negative quantity. All right, so take a square root. Rho is equal to 3 over the square root of 1 plus 3 cosine squared phi. And there we go. Beautiful. We were able to solve for rho, and we got it as a function of phi. So you give me any choice for phi, that's how far out you need to go. So for instance, if you say, well, what happens at phi equals 0, straight up? Well, cosine of phi is 1, so you get 1 plus 3 downstairs, and inside the square root it says 3 halves. They go up to 3 halves. All right, what about in the xy plane? Well, in the xy plane, phi equals pi halves. So that term drops out. It says go out to 3. So, we're 3 halves, then we're up to 3, then 3 halves downstairs. In some sense, it's a little bit more, almost like an M&M type shape, if you're looking for what this is looking like. All right, anyways, that's our first problem. We have more. Of course we have more. We love doing problems, because the more that we do, the better we get. Okay. Our next problem. Find the volume for the set of points satisfying z squared is less than or equal to r squared, which is also less than or equal to 4. Now this is a case where we have a string of inequalities, so we should start thinking about how can I break things up. So we say, well, what if I just was thinking about this? Z squared less than or equal to r squared. Well, if I'm thinking about what this is saying, that I can say, well, let's take a square root at both sides, because, get rid of the squares. When you take the square root, what does the square root of z squared become? And the answer is not z. What is the answer? It is the absolute value of z. So the absolute value of z is less than or equal to the absolute value of r. Because whenever you take a square root of a square, you're going to end up with a non-negative quantity. So you end up with the absolute value. Now, here's where I'm going to do something which you might object to, but let me explain it. When we talk about r is a quantity which is how far out we move away from the z-axis. That's really how r works. See, the z is how far up and down we move. R says how far away from the z-axis do we move. Now for z, it makes sense to talk about going both up and down. You can go in both directions. But when we talk about r, we really say we can go out. So really, you should think of this. This should really be r. We can drop the absolute value. Not with the z's though, because they can be both positive and negative. Now, whenever you're dealing with things involving z and r, I like to work in what I call the RZ plane. So let's think about what we can draw. Well, for starters, don't worry about the inequality. Just say, suppose you were told absolute value of z equals absolute value of r. Well, what you get are two possibilities. You could say, well, that says either z equals r or z equals minus r. So what you have is like an absolute value that's been turned on the side. Okay, now that's our shape. The question is, where do we shade? So how do we figure that out? Well, the way I like to figure that out is to say, let me just pick a point or two and test. So for instance, suppose I pick a point here. Well, what's true? Well, r is pretty, big. I can make it large. But z is 0. And 0 is less than or equal to a big number. That says I should include that point. Well, if I include that point, I include everything in here. Because the rule is, whenever you have these bounding lines, it really chops it up. And so anything that's in the same region, if you have a region and one point works, all points work. And if one point doesn't work, no points work. Well, what about these other parts? Well, if I pick something way down here, for instance, I can get r small, but z large. Well, that's not going to work. Similar up here, r small, z large. And so it's essentially the, if you like, the inside of this absolute value that's been turned sideways. Now that's just half of it. We got to do the other half. The other half is the other part of the inequality. So what is that? Well, that's the r squared less than or equal to 4, which means r is at most 2. Remember, when we talk about r, it should be a non-negative quantity. All right, so what is that telling us? If we sketch in the RZ plane, r equals 2, well, that's just here. And now, if I want to be less than or equal to that, that says, hey, I'm taking everything where r is smaller than that. So I have that. And now, what we do is combine. So we take these two ideas and we put them together and we say, all right, what we end up with is the following picture. And you can start to see what it is, I think. And hopefully you're starting to get your geometrical intuition building. What we have is essentially, it's like a triangle that's been turned sideways. And now what we want to do is we want to take this triangle, it's filled in, and that's a slice. In particular, this is a one slice for a choice for theta. And we want to say, okay, what does the whole shape look like? So to answer that question, now we say, well, our original inequalities had no thetas at all. See, there's no theta up there, which means that to get the shape, we spin. So we spin it around, and we say, all right, what's our shape look like? So the shape that we're after will have sort of the following configuration. It's this shape. Well, what is that? Well, what it is you can think of it as a cylinder, but then what we've done is we've popped out a cone on the bottom we popped out a cone on the top. All right, good. Well, now we just got to figure a couple things out. Well, we know what our r is. We know r is 2. So that says the radius here is 2. The top part would have z equals positive 2, because we're on this r equals z. And the bottom part would have z equals negative 2. So this length to go halfway down is 2, and the length to go all the way down is 4. So now we're ready to put our pieces together. Because what are we after? Well, what we've done is we figured out what does our shape look like. Cylinder minus some cones. Well, that's a stepping stone to say, okay, what's the volume of our shape? So our volume is we're going to take our volume of our cylinder, and then we're going to subtract out 2 volumes of cones. Now the cones, by symmetry, have the exact same volume. So that makes it a little bit easier to take care of it. 2 birds with 1 cone. Wait, no, that's not the same. All right, so how do you find the volume of a cylinder? Well, that's pi, the radius of the cylinder, squared, which is like the area of the base, times the height, minus 2. Now, how do you find the volume of a cone? Well, that's 1/3 the area of the base, so pi, I'll use a little r squared, and the height of the cone, h. So, what do we have? Well, radius of the cylinder is 2, and the height is 4. So pi, 2 squared, and 4, minus 2/3 pi. Radius is still 2, so 2 squared, and then the height is 2. So, well, that's 16 pi. And then here we have minus 16/3 pi. And, all right, because, 2 times 4 times 2, 16. And if you put that all together, oh, that's like 48/3 minus 16/3, giving us 32/3 pi. And there we go. There we go. That's it. All right, good. Well, let's try another problem. Of course. So, sketch the region consisting of points which satisfy phi goes from 0 to pi4 and rho goes from 0 to 2. Also express the region in terms of cylindrical coordinates. So we need to sort of figure out, what does the shape look like? And then once we have that figured out, all right, what is it going to look like when we go into cylindrical? Now, for helping us to figure that out, let's start by sort of breaking into parts. So there's really 2 parts. There's the phi part, and then there's the rho part. So let's start with the phi. Now, what's happening with phi? So when we say that phi goes between 0 and pi over 4, well, what that's telling us is how far off we come from the positive z-axis. So phi equals 0 is pointing straight up, and then we start to come down. So if we sketch what our picture here is, we say, all right, well, in terms of our shape, that would say we want to go from phi equals 0, which is straight up, all the way out to phi equals pi4. So we come out 45 degrees, or pi4. Now, of course, you don't just come out in one direction, you go out in every single direction. And so when we say phi equals pi4, we're really talking about a cone. So our shape would be a cone. So there we go. Now, of course, phi can be any angle in between. So ultimately, when we talk about phi being between 0 and pi4, it's everything above that cone. And so we get this region that we're dealing with. All right, and there's no limit to how far up we go. So for right now, it's just forever and ever and ever. Okay, so that's the first part, the phi part. Well, now we need to talk about the other part, which is the rho part. Okay, so let's focus on our rho. 0 less than or equal to rho, less than or equal to 2. So what does that look like? Well, we start by drawing our axes. Here's our space. And we think about what rho measures. Rho says, how far are we from the origin, the center? Well, it says, look, you can start at 0 and go out and out and out and out until 2. So rho equals 2 is a sphere of radius 2. And the fact that we can start from 0 out to 2 says that what we're looking for right now is everything that's inside a sphere of radius 2. So here's our 0 less than or equal to rho, less than or equal to 2. And so there we go. Now, remember, what do we have? Well, we have this word, and. Now, when we see the word and, that means that both things must be true. Our value for phi and our range for rho. So, it's like if you've ever seen those sort of three-dimensional where you cross your eyes and and all of a sudden say, whoa, I can see 3D. That's what we want to do. We want to say, now, overlap these two together, and what do we get? So, when we combine these two ideas, what we'll get is a shape. We say, well, it's like we're taking our sphere, but we only want the part of the sphere that's also inside that cone. Or another way to say it is we can start with our cone, but we only want to go out to distance 2. Whichever way you want to think about it, that's fine. But the moral is, what do we look like? Well, we kind of have the shape where we go out until we hit the top of our sphere, and then we have this rounded top part. So this part is our cone, and then this top part is our sphere, and our region is everything that's inside. So that's what our shape looks like. Now, one way you can think of it is if you've ever had like a ice cream cone as a kid, one of the things you sometimes might do is you like to sort of make that top nice round dome shape. And that's what we have there. All right, so there we go. There's our sketch of our region. So that's kind of a nice shape. And notice that in terms of spherical coordinates, a very beautiful description. We're saying, well, phi does this, rho does that, and now that's our shape. Okay, well, we're halfway done. Now there's another part. Also, it might get interesting now. Express the region in terms of cylindrical coordinates. Now, let's take something to our advantage. When we look at this shape, we notice that there's this beautiful symmetry around the z-axis. It's almost like it was a top that you could spin, and you wouldn't notice if you spun it on the z-axis. It would stay the exact same shape. Well, that really tells us we can make progress and understand what the shape looks like by looking at a slice, a cross-section. And so that's our next step, is let's go figure out what's happening in a cross-section. So the cross-section, you can imagine that we're going to just come along and just slice down. So slice, slice. So when we do that, what are we going to see? Well, what we'll see here, we'll have R and Z as we slice. The cone, well, that's easy to figure out what that's going to look like. That's going to be a line. It comes out at a nice 45-degree angle, which means this is Z equals R. The sphere, well, if we slice, what does a sphere become? The answer is when you slice a sphere, you get a circle. So you're going to get a circle with radius 2. So there's a 2, and it's going to come down. All right. So that's our cross section. Now, what's the formula? Well, z squared is equal, z squared plus r squared equals 4. There we go. Z squared plus r squared equals 4. Sort of like x squared plus y squared equals our radius squared. Because it is. That's exactly what we're doing, just in a slightly different setting. And now, it might be helpful, in that it will be helpful, to ask ourselves the question, where is this? What's the radius where these two curves are intersecting? Well, if we know that z equals r, that says that at the intersection, r squared plus r squared equals 4. So I'm replacing the z by r, which says that 2r squared equals 4. R squared has to be 2, or r is the square root of 2. So that says that this intersection happens at square root of 2. Now we're ready to describe what happens. Because there's no theta dependence, we don't have to do anything about theta. We just won't throw anything at all involving theta, which implies that we have that nice symmetry. So I need to describe this in terms of r and z. We have that we can take our region and describe it and say, well, look, what's happening to r? Well, we're starting at r equals 0 and going out to where that intersection happened. So 0 less than or equal to r less than or equal to square root 2. Now, suppose I happen to know which value of r I'm at. Okay, so I've picked my value for r. Now, what's happening for z? Well, what's happening is we're going to go in between the two curves. So we're going to go from r equals z, or z equals r, up to this top curve. So we already know what happens for r, so our goal now is to understand z. So where do we go between? Well, we start at r, so r is less than or equal to z, is less than or equal to, and now the top curve. Well, z squared equals 4 minus r squared, or z is the square root 4 minus r squared. So z is less than or equal to the square root of 4 minus r squared. And that will completely describe our shape in cylindrical coordinates. And there we go. Good, good. Now this ability, by the way, is going to be important later on, which is why we want to start thinking about, okay, how do we describe things? Cylinders, cones, spheres. We want to be able to move back and forth between different coordinate systems when we're working with those types of shapes. All right, well, let's see if we can do one more. How hard could it be? And other famous last words. So here we go. This problem deals with a solid formed by 1 over root 3r is below z, and z is below 1 plus root 3 minus r squared. So there's two parts, part A, part B. Part A, what's the volume? And there's lots of hints about, hey, here's various pieces of ways to compute volume. And part B says, go to spherical. Okay, well, that one should be interesting. That should be very interesting. Okay, so let's get into it. So what do we have? Well, so let's start with part A. Now, again, there's no theta dependence. We've seen that on a lot of problems. And that often happens when you're dealing with problems with cylindrical or spherical coordinates. It means you have that nice symmetry around the z-axis. It's great for symmetry around the z-axis. So we'll start by saying, well, let's just understand what's happening here. So I'm going to sketch. Here's r, and here's z. So z is greater than or equal to 1 over root 3r. What is that saying? Well, z greater than or equal to 1 over root 3r, we can think of this as something like a line segment because it's a line segment. When we start at 0, we're at 0, and our slope is 1 over root 3. It's a little shallow, so it's coming at a, slightly shallow slope. So this is z equals 1 over root 3r, and we want to be above it. Now, when we think of the three-dimensional shape, this line segment becomes a cone. So we're inside of this cone. We'll get into figure out what that cone is a little bit later. Now, what about the top? Well, for that one, let's think about what we can do. It's kind of written in a strange way, right? So we have z is less than or equal to 1 plus the square root 3 minus r squared. It's not so clear what that is. So let's start by saying, well, what if I just had z equals that? That would maybe help us figure it out. 1 plus the square root of 3 minus r squared. Well, we start rearranging things. Well, what we'd like to do is get rid of the square root. That's oftentimes a great first step, is to get rid of that square root. So we could say, for instance, z minus 1 is equal to the square root of 3 minus r squared. And now, if we square both sides, we could say, so this becomes z minus 1 squared is equal to 3 minus r squared, or r squared plus z minus 1 squared equals 3. Now, this form, it's a little bit more clear what it is. Now, if you're not comfortable with r and z, think in terms of if we call these things x and y. If I said, hey, it's x squared plus y minus 1 squared equals 3, what would you say? You would say circle. So now instead of using x and y, we use r and z. What do we have? It's still a circle. So what can we say about this circle? Well, the center starts at z equals 1, and then it has a radius of root 3. And I should point out r equals 0. And so we have this sort of radius of root 3 coming along somehow, and some way, I don't know exactly. And so this curve right here, notice it's the top part of the circle. It's because it's the plus. So this is our curve z equals 1 plus the square root 3 minus r squared. Now, the question, where do they intersect? Well, good question. Good question. So, to make progress in that, what can we do? Well, when they intersect, suppose I were to solve for r. I know that at the intersection, r has to equal square root of 3 times z. So, I can come along to, well, let's see, where can we put progress here? All right, let's go to here. What do we have? We have r squared, which when we square that becomes 3z squared plus z squared minus 2z plus 1 equals 3. So I'm just taking this equation, multiplying it out, and replacing what r is. So, well, that says 4z squared minus 2z and minus 2 equals 0. We put the z squares together, subtracted the 3. Now we can divide by 2. 2z squared minus z minus 1 equals 0. All right, we're making progress. Can we make even more progress? Yes, because this will not surprise you. It factors, almost like we wanted it to, because we wanted it to. So it factors as z minus 1, 2z plus 1 equals 0, which leads us to two possibilities, z equals 1 or z equals minus a half. Well, it's not going to be negative a half because that's not, the picture won't allow it. So it's going to happen at z equals 1. So, aha, perfect. So indeed, it's going to be here. This is actually the top quarter of a circle. Perfect, perfect, perfect. And now we know that that's z. What about r? Well, we know that r is root 3 times z, so this becomes root 3. Good, good. So now we have a good idea of what our basic shape is going to become. Because what's going to happen is our region in the sort of RZ slice is this piece right here. And now what's going to happen is we want to spin. And by spinning, we'll form our shape. So what we get is that our shape in 3 dimensions looks like the following. It's a cone, and then there's a half sphere on top. It's not like it's a part of a sphere, it's truly a half a sphere, because the center, again, the center, that's exactly where we make the cutoff. So it's a hemisphere, half a sphere, on top of a cone. So we say, great, perfect. We have ways to find things like spheres and cones. So we're in business. We're in business. So we say to ourselves, okay, what do we do? Well, we say our volume is 1/2 the volume of a sphere, because that's the top part, plus the volume of the cone. That's the bottom part. So for a sphere, we have our formula. That's 4/3 pi. And now we just need to know what's the radius. Well, so what is our radius? We know. It's actually here. See, we can see it. This is r squared. So we have the radius is root 3. Well, let me not use r. Let me use radius. So we'll have square root of 3 cubed. Good. Plus, of course, the volume of the cone. Now, how do you find the cone? 1/3 pi r squared h. Now, r being the radius, not the r as in the cylindrical coordinates are. So, plus 1/3 pi. Now, what's r? That's how far out we come. So it's square root of 3 squared. And what's h? It's how high up we go. It's 1. All right. So, good. Good. So, what do we end up with? Well, the square root of 3 squared is 3 times 1/3. Cancels. So this last part becomes just pi. Now here it's a little bit more interesting. The 2 goes into the 4. That's great. The square root of 3 cubed, I can think of it as 3 square root of 3's. 2 of them will combine to give me a 3. And I have 1 square root of 3 left over. So I can cancel 2 of the square root of 3's with the 1 3 downstairs. So we end up with 2 root 3 plus 1 times pi. And that's the volume. Good. Part A, done. Done. Now, if you look at it, it's actually not so bad. It's just a matter of saying, hey, let's understand a cross-section. What does it look like? Well, it's a triangle on top of a sort of a part of a circle. When we spin it, it becomes a cone on part, and on top is a hemisphere, half a sphere. And then we're like, okay, good. Well, okay, figure out half of the volume of the sphere, figure out the volume of the cone, put everything together. Life is good. And we're happy. All right. Well, there's a part B. And part B is going to be even, I think, a little bit more fun. Okay. So, round 2. Here we go. We'll clear some work here, because really the main thing we need to focus on is this picture. So let's think about our picture here. What can we say? Well, the reason I'm focusing on the picture is we still don't see any theta dependence. Theta does the same thing in both cylindrical and spherical, which means I really just now have to focus what's happening with phi, what's happening with rho. So let's talk about phi. When we talk about phi, phi is about how much you go off the positive z-axis. So the answer is we're going to keep going off the positive z-axis. We start at phi equals 0, and we're going to keep going until we hit that angle. See, that angle is when we stop. When we go below that angle, we're no longer hitting any of our shape. We're just completely missing it. So what we need to figure out is the question, what can we say about this angle right here? Well, let's take a look. We know that this z is 1 over root 3r. So when we did some really quick computations, we saw, for instance, if we went all the way out to r equals root 3, then when we looked at the height, we got to 1. So we're starting to say, all right, so if this is our angle phi, that's also our angle phi. So this angle here matches that angle there. And we say, okay, I know the opposite side is root 3, the adjacent side is 1, so the tangent of this angle would equal root 3, opposite over adjacent. Well, that's not just any angle that does that. That's actually a really well-known angle, and I'll go ahead and tell it to you. That's pi thirds. So tangent of pi thirds is root 3. If you're not familiar with pi thirds, it's also 60 degrees. And you can say, okay, 60 degrees, that seems right. It looks bigger than 45. Definitely it's below 90. So 60 is sort of our go-to angle in that range. So what can we conclude about phi? So our conclusion about phi is that phi will start at 0, and it'll keep going until we hit pi thirds, and that's it. That's all we can say about phi. So we have that 0 is less than or equal to phi is less than or equal to pi thirds. That's part of it. That will make sure we're within the cone. Now to the other part. And here's where things are going to get fun. Let's talk about rho. When we think about what's happening with rho, the philosophy is you start at the origin and you move out. So we're going to start at the origin and we're going to keep moving out until we hit something. And we're always going to be hitting essentially the same thing. It doesn't really matter which direction we go. What we hit is that sphere, which, and when we look at the cross section, is really a circle. So what we need to figure out is how far do we have to go until we hit that sphere/circle. Okay, so we're going to think about the following. We have the surface. Z equals 1 plus the square root 3 minus r squared. That surface, we need to rewrite that in terms of spherical coordinates. So, how do we begin? Well, we replace what we know. We start by saying, okay, z, that's rho cosine phi. We'll move the 1 across. Minus 1 is equal to the square root of, and then we have 3 minus, and an r is rho sine phi squared. This is very similar to what we were doing before. All we've added in is what is z and r in terms of rho and phi. Square everything. So we'll get, when we square this side, rho squared cosine squared phi minus 2 rho cosine phi plus 1, that's the square of the left, equals 3 minus rho squared sine squared phi. All right, now from here, what can we do? Well, there's really only two logical things to do, and they are to move the 3 over and the rho squared sine squared phi over. Because we want to sort of, whenever you have an equation, it's nice to get rid of square roots. And once they're gotten rid of, shove everything to one side, because that gives us something equals 0. We like to incorporate 0 whenever we can. Now, when I bring this rho squared sine squared phi over, it's going to combine with rho squared cosine squared phi, and putting the two together, I'll have cosine squared plus sine squared, which is 1. So we get rho squared minus, all right, this says 2 cosine phi times rho, and then 1 minus 3 is minus 2 equals 0. Good. Good. All right. Now, what do we need? We need to solve for rho. How do we do it? Well, notice what do we have? We have a quadratic equation involving rho. So the way we solve for rho is use the quadratic formula. So we get that rho is equal to negative b, which would be this negative of negative 2 cosine phi. So 2 cosine phi plus or minus the square root b squared 4 cosine squared phi minus 4ac. So 4 times 1 times minus 2 be plus 8. All of that all over 2a, which is 2. Now, quick side note. Do we need the plus and the minus? And why can we get rid of the minus? So the answer is we don't need both. We only need the plus. The reason we can get rid of the minus is we think about rho as being a distance out. So it should be a positive quantity. Currently, if you look at what we have, the 2 cosine phi, if we tried to subtract that expression, it would be a negative quantity. We don't want negative quantities. So we want the plus, which is good. Now, the other thing we can do is say, hey, let's cancel the 2. And notice how everything inside the square root has a factor of 4. We can pull that factor of 4 out and really all the way out in front as a positive 2. So that can also cancel. So we get the bounding curve, this bounding curve here. Rho as a function of phi becomes rho equals cosine of phi plus the square root of cosine squared phi plus 2. All right, good. Now, you give us any choice for phi, that's how far up we go. At this point, you're probably thinking, wait a second, hold on. I thought rho would be nice because we're dealing with spheres and this is spherical coordinates. Well, the thing about spherical coordinates is great when your sphere is centered at the origin. When your sphere is not centered at the origin, it becomes dicey and, as we see here, kind of messy. So be careful, be careful. Now, we're almost done because we had to say rewrite the bounding surfaces as equations in terms of spherical coordinates. We know what happens to phi. We now know how far out to go for rho. And so the last thing, and I think we'll just move this up a little bit here, we'll fit it in, is to say, all right, that says we need to start at 0, which says start here and keep going. So the way we say we keep going is say we'll have rho starting at 0 and going up till we hit that bounding surface, which is the cosine phi plus the square root of cosine squared phi plus 2. And that is our second equation. So these two equations are what happens to describe that region in spherical coordinates. Okay, wow, what a doozy, what a doozy. A great way to finish, and I hope you had fun, hope you survived to the end. And this one's more challenging than many problems you might encounter, but it's good to do challenging ones because that's how you develop. You develop your skills, you develop your intuition, and then once you can do the challenging problems, the other ones don't seem so bad. And that's what we want. We want to be comfortable in doing the ones that we encounter. All right. Well, thanks for hanging in there. See you again.